Okay, good afternoon, everyone. Welcome to the Materials Valley online seminar. Today, it's pleasure to have our speaker being Dr. Sam Cooper from Imperial College London. So then, a very brief introduction about him. Basically, he started mechanical engineering already in 2008, and then continued with his PhD there in the Department of Materials. In Imperial College London, and then afterwards he had a postdoc position somewhere with Professor Nigel Brandon, and then in 2017 starting his own group there in Imperial College London again till today, I think. So then what is kind of noticeable for me is 3 years ago he launched a small startup which is called Polaron, and then as he mentioned earlier today, if you are not aware, so then he is working there instead of taking a holiday. And then another some point I want to mention is, after checking the publication and so on, I realized that he has, he is the co-author or the author of this very nice paper or tool called a slide scan. So this is something which kept me fascinated for a long time. Even nowadays, I'm thinking of using this to really get the 3D microstructures generated from 2D snapshots. I hope then there will be some reports from him on this subject or some updated version. Yes, so then I think that's all from my side. Without further ado, so Sam, stage is yours.
Great.
Yeah.
Thanks, Hongmin. Okay. Well, good afternoon, everyone. Um, so the talk I'm going to give you today is roughly in two parts. So the first section is talking about our historic work around microstructure. And then the second half is a kind of broader view of some of the activities we're doing in AI for science. And hopefully we'll have plenty of time at the end for some questions and discussion. So microstructure, of course, applies to many material science problems, but I've always been particularly interested in electrochemical energy systems, so batteries and fuel cells. And just to give you a sense of why microstructure is important, here's a kind of view. So inside a typical lithium-ion battery, you've got what's called a jelly roll. So this wound up set of sheets where you have anodes and cathodes separated by separators and backed with current collectors. And the point is that in order to liberate energy from the system, the lithium ions need to escape from a particle of graphite, travel through the pore network of the anode and the separator and the cathode, and enter a particle of the cathode active material. And the wiggliness of those pores will, in effect, slow down the transport of the ion and therefore create an over potential and reduce the amount of energy you can extract from your system at a particular power. And in order to increase the amount of energy stored in the cell, we want to pack in as much active material as possible, but the more you pack in, the less pore space you have to facilitate this ionic transport. So as with so many systems, there are competing factors that need to be considered in order to optimize them for performance. I'm based in the Dyson School of Design Engineering at Imperial, and as such, we try and frame a lot of the problems that we engage with as design cycles. And so you can think about this as a kind of design cycle where we go from having a sample that we characterize, perhaps using some kind of microscopy technique, in this case, SEM imaging, and then we want to turn that image into a map of the distribution of phases. So we've done some kind of segmentation, and then we move from the segmented model to perhaps use a physics-based model to understand the relationship between structure and performance. And then ideally, we'd like to start moving backwards. So how can we modify the structure in order to achieve improved performance? And then finally, we can make and test this improved sample again to see if we've achieved what we predicted. So here is an image of a lithium-ion battery cathode material. And the image is about 100 microns thick. So the electrodes are about 100 microns thick, and the particles inside them are roughly 10 microns thick. Obviously, many of them are much smaller than that. In between the particles of active material, you also have a sort of fuzzy carbon binder domains. That's a mixture of a polymer that holds everything together and some carbon black that facilitates electronic transport. And then you've also got some void spaces, so some regions in which there are that will be filled with the ionically conductive electrolyte inside the combined cell. So one of the problems that we're trying to resolve here is once we've got this image from our microscope, we then like to go to every pixel and allocate that pixel to a particular phase inside the cell so that we can start to do some physics-based simulation. There's been huge advances in computer vision in the last 10 years, mostly resulting from deep learning capabilities. And one example of this is the Dino V2 foundation model. So typically for foundation models, you focus the architecture and the training strategy around somewhere where you happen to have lots of data, and then you hope that this very rich model can then be applied to some specific applications down the line, even though it wasn't necessarily trained directly for that thing. So that the justification or the motivation for foundation models is that let's think about where we do have lots of data, then afterwards let's think about how the resulting model could be used to solve a particular problem. And what you saw in that brief little video, which I'll play again, is a dog running around, and this foundation model or a similar foundation model has been trained on the task of, for each still in an image, right, and this is for billions of images, what you need to do is cover up lots of patches of this image. So cut the image into lots of patches and cover some of them up and pass them through a vision transformer. And the task of the vision transformer is to fill in the patches that were missing, right? And you can imagine it's easy for a human, or not easy, but it's possible for a human to do this, where if I give you a photograph and I black out some patches, it might be possible for you to paint back in with a nice paintbrush what was cut out from the data. It turns out that asking a model to perform this task across billions of images forces it to learn some fundamental structure about reality, right? And so what you see on the right-hand side is the first three principal components put into RGB of the feature space, so the sort of representational space of reality that this self-supervised model has learned of its own accord. So it's never been told about the concept of a dog's leg, and yet it's colored them both green because it knows that both those things in the image are the same type of thing, whatever that type of thing is. This is very useful because we can take those featureization, those feature stacks and pass them into classification models in combination with some human-based labeling from image data and use those to do really high quality, high accuracy segmentation of images. However, the images that typical vision foundation models have been trained on are what are typically called natural images. These are photographs of the world. And photographs of the world tend to have structure. They have an up and a down, a sky and a ground. And this means that one way, often for a model to quickly work out what something is to have a look at where it is in the image. If it's near the top, it's probably the sky. If it's near the bottom, it's probably the ground. However, in microstructure, there is no up and down, top and bottom, or not in the same sense, at least. And so this means that these vision foundation models often come with biases that we need to remove in order to do materials or in order to apply them to material science applications. And what you can see here is results from the Dino V2 model, where we've been able to probe and extract the signals from the biases in the images. And what we can see is that, like, particular channels in the features. So I think there's, roughly 400 in the feature stack that roughly channel 120 and roughly channel 50 have very strong correlations with a pure left-right bias. And this is something that would propagate through to our segmentations and cause things in the left of the image to be segmented different from things in the right of the image unless we remove it. So that the dino is, in a sense, confused about reality once you take it to the micro scale. And this we can very clearly see when we propagate it onto some real microstructure examples. As well as thinking about the algorithmic design, we also think about how to modify the imaging strategy in order to align better with the capabilities of deep learning. And what you can see here is the same sample imaged in quick succession using 3 different detector modes. And what you should notice is that the pores, in this case, a very large crack in the sample, are getting darker as we change the detector mode. And this is indicative of the fact that the objects inside that crack are not on the surface. They're not on the imaging plane that's been prepared with a broad beam ion mill. And this is very often something that we need to cope with in imaging porous media. We don't want the things that are in the depth to be considered to be on the imaging plane. Otherwise, that will mess with all of our statistics. Having these kind of multi-channel images, you can pass the whole channel stack through to your deep learning based image analysis platform, and it will work out just as you can with your eyes now, that some things are not in plane due to the fact that they get darker in a sequence of images. So here's our nice image of a cathode again, and I can overlay the deep learning based vision transformer featurization stack on top. Again, it's just PC 1, 2, and 3 stuck on top. And then I can pass those to a classifier and use those to get a really high quality segmentation of the image. And again, with an anode of graphite and silicon in it, and I can use that to generate some really high quality segmentations there as well. Another nice approach for improving your imaging capability, we came up with a few years ago called kintsugi imaging. So the top row, we see preparation of a sample as normal, but then we cover over the imaging plane with platinum and polish away the platinum again to get back to where we were. And now you can see that all the cracks have been filled in with platinum. And this gives you a really strong contrast agent, essentially, and allows you to work out where the pores are in your segmentation. And as I mentioned, these image classification problem has been around for a long time, and there have always been classical features like human-specified features like edge detectors that people could use for segmentation, but these have some real weaknesses. How can you tell the difference between a long, thin object or just the edge of a not long, thin object? Deep features are able to get this much more holistic view of all the structure of an image and identify those things with a lot more confidence and consistency. In general, in my team, we try and turn all of our creations into tools that other people can use. So this is Samba Segment, where the segment anything model is being used to turn single clicks into patches of labeled data, and then the user can color in other parts and then apply a classification model. I think this is using XGBoost to apply what's been specified with the labels across the whole image. And for lots of the work that we do, we're really keen to get access to high quality data, but often it's not available. And Dr. Anthony Van Verklos has, in collaboration with Ronan Doherty, have put together the batteryimaginglibrary.com. And this is a massive database of battery imaging data from microstructure, from atom probe all the way through SEM, TEM, all the way up to X-ray computed tomography of entire cells, vast amounts of it, all openly available and sort of searchable in a delightful Skyscanner style flight booking platform where you can say, well, I wanted to have a resolution in this range and I wanted to be of this size and I wanted to use this imaging technique. So head to batteryimaginglibrary.com now to get your data. A topic that we care deeply about is representativity. So very often you've imaged your sample as best you can, but then you want to know, and you've processed it and you've extracted metrics from it. You want to know, considering the image that I have, how close would I expect the metrics that I've observed to be to those of the bulk, the sort of infinite bulk of the microstructure? And what this nice illustration shows is the idea of sort of progressively zooming out on a sample, a two-phase sample. And what you can see on the right is the average phase fraction of that image. So what percentage of the image is white as we zoom out? And you would hope as you get larger and larger or you zoom out further and further, this should converge to a value. But generally, you will only collect one image. So how do you know where to look? And we have published a method that you can get from ImageRep, where you can pass in a single image and using 2-point correlation statistics extracted from a fast Fourier transform, you can work out your confidence interval. So you can put in a single segmented image and say, this image is 37% porous. With 95% confidence of being within X% of the true value of the bulk material. So it's a really useful way of getting a sense. And it will also say to you, if you wanted to be 95% of being at 1%, this is how many more in the same size you would need to collect. So it's really useful. A little depot here. It's another kind of web app that you can make use of today. So here's a sample of how it goes. So once you've imaged your data, you've segmented it, and you've checked for representativity, next, certainly for our team, we wanted to try and understand if we could learn the core underlying statistics of that image. And so about 5 years ago, we started playing with generative adversarial networks. This is where you get two deep convolutional neural networks to compete with each other. One network takes in little patches of your segmented image, and it's trying to give them a high score. It's trying to say, in comes an image, and I want the output to be a high number to show that I believe it's from the training set. And the other network, its job is to take in some randomness and give out a fake image, and that image is then passed into the first network and try to just trick it into giving it a high score when it should really give it a low score because it's a fake image. And you make them talk to each other with a bit of maths, and this allows you to adversarially train two networks. Eventually, you should have a generator that is able to confuse the discriminator, as it were. Once that generator is trained, you can then generate arbitrarily large volumes of data, much bigger than you could ever hope to image with a microscope, and use these as the domain for physics-based simulation. About a year or two after that, Steve Kench joined my group and worked out a method for generating 3D microstructural volumes from 2D data. And so this means if you assume that your data is isotropic, the same in every direction, you can pass it a single 2D image, and it will then generate for you 3D volumes, which is a very useful thing because 3D imaging at the microscale is very slow. So basically, X-ray computed tomography is not able to image battery electrode microstructure. It can't see the difference between the carbon binder domain and the pore. And so you end up with active material particles floating in a sort of fuzzy free space, which is not good enough to understand their relationship between structure and performance. So you need to image them with FibSem, but FibSem is very arduous, right? Even when you are a master, it still takes a long time. And so getting a representative volume in 3D could take you 3 or 4 days on a £2 million microscope. Or a single wide cross-sectional image that's just 2D can be collected in about half an hour on the same microscope. So it's a 2 order of magnitude speed up in acquisition time. And then you use this single 2D image to train a 2D to 3D generator, and you've got what you need. You can use very similar technology to do things like in-painting. So if there are missing or damaged regions in your data, you can fill those in. And you can also do things like data fusion, so combining multiple modes imaging. So combining high resolution SEM imaging with low resolution XCT imaging, a wide field of view, but high resolution combined image. And what you can see on the bottom row is just little patches from the top row, is that the output is the same structure as the low res, but the same statistics as the high res. And that's exactly what's happening during the data fusion. And we can validate all of this stuff. So all of the techniques I've showed you, they very easily pass the human eyeball test. They look real, but that's not enough, of course. So what you want to understand is, do they have the same metrics, the same statistics, and which ones? Well, which ones do you care about? So we can show that both in terms of the mean and the distribution statistics, it is very similar to the ground truth for things like volume fraction and surface area. But more excitingly, it's very similar to the ground truth for more elaborate metrics like transport simulation results, like tortuosity factor. And so what's nice about this example is, in the data fusion sense, tortuosity factor was not calculable from either the 2D input or the 3D low res input, because the 3D low res was actually missing one of the phases. So you can't get it from either of the training sets independently, but you could extract it really well from the combination. All the techniques I've shown you today are stochastic. So here's it generating a sort of super resolution of a 2D region, but I can make another one, and they are globally very similar. But if I look at a particular region, they are locally quite distinct. And I can keep generating these all day, and this can give me a sense of the impact of these local distinctions on my global simulation results. Ideally, you wouldn't want a simulation to be very sensitive to a particular generation. Once you've generated your 3D microstructure, of course, then you want to extract performance relevant metrics. So if you're a battery, this can be volume fractions, surface areas, effective transport metrics. However, some structures are intrinsically graded, and really basically all battery electrodes are graded to some extent in the sense that their microstructure varies as a function of depth through the electrode. So the microstructure will be a little bit different next to the current collector as it will be next to the separator. And this can be inadvertent because you have it too quickly and the solvents have come off too fast, leaving the binder non-uniformly distributed, or it can be deliberate and you can improve the performance of your electrode because you need more electronic conductivity close to the separator and more pore space for ionic conductivity next to the separator and electronic next to the current collector. So Simon Darbner in my group, who's recently published a fantastic study around quantifying tortuosity as a function of depth through a sample, which cannot be done by putting tau through little subdomains, because eventually, if your subdomain gets smaller and smaller, tau will tend towards 1 anyway, which is meaningless in this context. So instead, he simulates across the whole domain and then applies a nice closure relation to specify tortuosity as a function of x. And what we've shown is that this can, by having volume fraction, surface area, and tortuosity as a function of EPS, you can use these to parameterize equivalent circuit models, like transmission line type models or Doyle-Fuller-Newman models, and really accurately reproduce the results of 3D simulations with just these 2D metrics, which is not possible with electrode average tau, epsilon, and A. So it's a really exciting result and really important for next generation cells. Most of the advanced cells today have multi-layer electrodes if you're looking at cells produced by CATL or BYD. And we can show this for graded cells, bilayer cells, and homogeneous. And we see that I think the first time anyone's reported a way of extracting tortuosity as a function of depth through your electrode. So it's a very exciting paper for me. And here you can see the impact that this has on performance. And this is a sort of Ragone plot showing the available accessible energy as a function of power for a cell. And you can see that the different systems, so the bilayer and the bilayer reverse, have very different accessible energy. So you look at the thick lines, the homogeneous cell, so the cell made uniformly, it's got about 40 watts, it's got about 7 watt hours. But if the bilayer is made badly, i.e. the wrong way around, you halve that. And if it's made well, you can add about 40%. So it's a really exciting result. Simon's currently got a fellowship at Imperial, a Schmidt AI for Science fellowship, and he's using this to develop eVoxels, which is a differentiable voxel-based physics solver library, which you can check out today. So to pull all this together, if you want to understand, if you want to improve the performance of a battery, first you've got to understand how the electrodes are made. So it's typically 4 steps: mixing, coating, drying, and calendaring. And in those 4 steps, you've got all kinds of physics going on. You've got solids, liquids, gases, you've got viscous flow, you've got phase change with the drying, and you've got fracture and deformation in the calendaring. But the state-of-the-art simulations tend to still look a little bit like this, which is dropping random spheres in a box. And this is because it's so much physics. It's just very, very difficult to solve. The reality looks, of course, like this. We saw some SEM images at the start, and it's much more complicated than the simulations. Our approach instead has been to take 3D microstructure. It's to take SEM images of different electrodes produced using different manufacturing settings and use those to train a single conditionalized generative model. And once that model is trained, you can do inference in seconds, i.e. you can generate microstructure very quickly, pass those to metric extraction software like tau factor, and use those resulting metrics to parameterize discharge simulations in something like PyBAM, and then ultimately use something like Bayesian optimization to search for optimized processing parameters for a particular desired battery specification. So this loop is only closable because the microstructure generator is roughly 1 million times faster than the physics-based equivalent from Sandia only a few years ago. So it's really exciting. And to look at this case study in more detail, if you want to optimize a 4680 cell at low power, which is 70 watts, well, the result says have lots of active material, not much carbon binder. That's the horizontal axis. And the vertical axis is saying don't have very much porosity. Why? Because for both axes, the story is the same. Transport is not very limiting at low rates. So you don't need much help electronic or your ionic conductivity sensitivity. But as power increases, these things become more important, and you can plot a path through parameter space showing you what your optimal cell design would be for a particular combination of demand. And you can generalize this to many more parameters that you might use to design a cell. And ultimately, you can check out sort of high energy or high power cells based on a range of manufacturing options, including things like the slurry composition and the calendaring metrics and the drying rates. This is what led 2.5 years ago to us spinning out a company, Polaron, and we now have an office in East London. There are 15 of us, and we sell software to manufacturers around the world, not just in batteries, but also in things like alloys and composites and basically anything where microstructure is important. And we were very fortunate that last year we managed to raise $8 million to scale the company and bring our software to more people as quickly as we can. So that's the first half of the talk, which is about the last sort of 15 years of work focused on microstructure. And the second half is shorter, but just to give you a sense of where things are going. So Imperial has got a consortium led by Professor Magda Tirici, who are focused on autonomous labs for electrochemical systems. So our lab is called Digibat, and it is a robot or a collection of robots that can make and test batteries and battery materials. And you can see the suspicious blue gloves. Those are actually human hands, not robot hands. And so we are still in the process of closing the loop, but some of the steps still need a bit of human intervention. Being able to make such a large number of cells of good quality means that we need to think differently about how we collect, process, and view our data. So we've developed some software called CellSeer, which sits at the front end of Data Lab, that allows us to search through very large numbers of cells quickly in a sort of web interface, and that all the data is like sensibly ontologized, and it can very quickly generate plots for large numbers of cells so that we can explore. And for example, if we find an outlier from its discharge data, we can work that back well in order to understand, maybe let's have a look at the mass during the cell assembly at every stage and see if it got a little bit less electrolyte than some of its adjacent cells. We've also been thinking about the structure of complicated projects in general. And this is some work from Shiz To and Felix Mildner, who have been looking at knowledge graphs as a way of representing large complex projects like a European research project, where you've got partners, deliverables, milestones, tasks, all these different things, and they interact in different ways and they have different connections. Once you have a representation generated automatically from your proposal using an LLM, you can then also use an LLM to query your knowledge graph and listen to all of your meetings as you progress with the project and generate meeting minutes, and then update the knowledge graph with the meeting minutes so that any project partner can log into the sort of Project Central website and have a conversation about the current status of the project. So that's very satisfying as well. We've also been using LLMs for much more targeted scientific tasks. And this case study is about the design of charging protocols for batteries. And so if you want to charge your battery, you control your voltage and your current, and different strategies can result in the same ultimate charging state, but with different amounts of degradation caused by it. Okay, and so how do you go about designing a optimum charging strategy? And probably the most famous paper on this topic simply uses a set of 4 constant current phases, and 3 of them are free parameters, and the 4th one is derived from the first 3. And it shows that you're able to search for an optimal strategy. But of course, 3 specifiable parameters is not a very expressive functional space. We've instead used a large language model to write the code so it writes some PyTorch, some Python, to specify a small neural network, which is a much, much more expressive functional space, and then use Bayesian optimization to find the parameters of that network in order to search for optimal charge strategies for an arbitrary cell. And what we found is it works very well indeed. We've also been using large language models as agentic systems in harnesses to control autonomous science workflows. So this is Maestro, the materials acceleration engine for synthesis, testing, research, and orchestration, which is from my student Shiz To, who is an A-star scholar, who's been trying to reproduce some of the papers that we've historically published using this agentic workflows, but in a sort of conversational way. So The agent is aware of the lab context in which all of this work is being done, and it's able to call functions that are available to it. So tested sample making machines and sample testing machines and optimization algorithms and memory and pursue a study that the user has specified. So finally, I want to talk a little bit about LLMs in more detail and the way that they are designed and the way that they operate. And so some of you might not know so much about them. They are transformer architectures. That's what these large language models are typically based off. And transformers take large cannons of text originally, but now it's text and images and other things. But you take text and you chop that text up into tokens. Those can be words or pieces of words or just letters and symbols, and allocate them to a particular token space. So that there's your token space, and each word or piece of word is somewhere on that list, right? So the word "the" is element 464 on that list, and you then embed it by multiplying your token vector by an embedding matrix, and then you apply many layers of the same operation. And each operation basically has two things going on. You've got attention, and there are various types of attention mechanism, but broadly speaking, each token corresponds to a little vector at that particular layer, and you can calculate, again, if you wish, just from a matrix multiplication, three new vectors from this vector: a key, a query, and a value, and K, V, and Q. And your local token, the one that you're currently at, which in our case is because it's the most recent token to be looked at, its key is then compared to its query is compared to the key of everyone else, all the previous tokens, and then whether it scores a high score weights the extent to which its V vector is then applied to the last token. So that's a way of extracting information from all the previous tokens, and then you also pass it through a multi-layer perceptron, so just like a big neural network. And this is also another way for information that is stored locally within the machine. So once you've applied that process many times, so you're iteratively transforming your vector. The vector stays the same size, but you apply this nonlinear transformation lots of times. Eventually, the final vector is spit out and put through some kind of vocabulary head, so a way of converting that token into a word. And typically what that will be is comparing that vector, that vector will pass through some kind of transformation that will cause it to be compared to the vocabulary space, i.e., it will give a percentage or a likelihood of that token belonging to one of the possible tokens that's from the vocabulary space. So in this case, it's saying there's a 21.59% chance, as it were, that the next token should be the number 6, which of course the atomic number of carbon is 6. And so this is its way of expressing what it thinks is about to come next. And models, you might have heard, they've got some randomness in them. Well, you might actually, instead of picking the top most likely one, you might say, let's roll the dice and pick one proportional to its probability of being the next token. So that's a very fast primer about how transformers work. Well, with looking inside that structure, we've been able to determine a few things. And one of them is that the Llama series models, released open source by Meta, have internal structure to their thoughts, which is not surprising. And this was already seen. For example, the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, are not in a line. They are, of course, a circle, because after Sunday comes Monday again. And this was shown a couple of years ago. What we have shown is that the periodic table of elements appear to be in a three-dimensional spiral structure, which is, again, not surprising. This is the correct conceptual shape for this set of ideas. So it's really reassuring to see that these models, which for these particular models have just been trained by reading loads of text about everything, have independently chosen or independently formed geometrical structures inside their own minds that do reflect the truth of reality. So it's a very exciting thing, because it means that you will have more confidence in their guesses about things that they haven't been explicitly shown before. We've also been thinking about understanding the belief states of large language models. So if I show a large language model some data, some limited data, in this case, if I just show it one data point, this little cross, I can actually query the model in a specific way to ask it what it thinks is probably going on everywhere else. If I just say there's one data point here, x equals this, y equals this, okay? For reference, there's a gray line, which is where my true data point was sampled from, but the model has absolutely no way of knowing that at this point, okay? So it's just actually put a weird little Gaussian bump in the middle, okay? Very arbitrary, and there's some very unstable behavior in some of its points as well. But what's interesting is that large language models, unlike any previous formal optimization technique, whether it's Nelder-Mead or Bayesian optimization on Gaussian processes, the special thing with large language models is that I can pass them additional information in the form of plain text. So I can say to a model, hey, here's one data point, and by the way, this is a single point extracted from a linear function. And you can see that all the points have now snapped to a line. Now, it's not the line, it's not the truth, but how could it possibly have known the truth anyway? Because I haven't told it. I can then say, hey, by the way, it's a line, and these are the parameters of that line. And the points now snap to the line. Okay. And if I confuse it by saying, oh, by the way, it's actually a parabola, it'll put a parabola through that point and make all kinds of mess, but it clearly won't access the truth. This is, in some ways, blindingly obvious, right? I tell the model useful information and it incorporates it into its belief state. But actually, it's quite hard to, I've not seen any numerical evidence of that before. And we've now got a really rich description of the model's current view on what's going on. And this is so important for the control of things like autonomous labs, where often you'll have sparse observations and lots of very complicated constraints about your lab, when the machines are available, what the machines can do, what their relationship to uncertainty is, all of these things, health and safety and resource capacity, all of these things in principle are being taken into account by the minds of diligent scientists, but we've never been able to pass that information to optimization algorithms before. Or some of it we have been able to, and some of it we haven't, and it's always been quite tricky. But now, in a sense, we can use LLMs as surrogate models and pass them this very poorly formed type of information. The very last thing I want to show you is about the way that the models seem to think about the world. So it's possible to extract the confidence that a model has about a particular guess that it's making. You could ask it, that's one way, but that's not necessarily very direct. The more direct way is to probe the token level confidence. So all the way back here, I showed you that it was saying that the next token confidence is 21.59%. Well, does that directly compare to human confidence? It's not clear what's human confidence anyway, but it is telling you something about the model's confidence in the next token. This graph is very similar to a pop psychology graph called the Dunning-Kruger curve. And what the Dunning-Kruger curve shows or suggests is that if you give a person a small amount of information about a topic, they can become very confident in their ability to predict and their understanding about that topic, right? Not accurate, confident. Okay, but if you give them a bit more information about it, they might see that the reality is more complicated than they've been assuming, and their confidence collapses. And then gradually, this confidence recovers as you give it more and more information. So this non-monotonic behavior is a sort of characteristic curve of psychology called the Dunning-Kruger curve. What we have shown is that these large language models have the same non-monotonic behavior. So you give them, if they've got no information, they know they're not confident. You give them a little bit, their confidence rockets up. You give them a little bit more, it collapses again and slowly recovers. So we don't necessarily know why that is, but we find it very satisfying that, of course, these robots are not thinking in the same way as humans. However, they do seem to have some of the same phenomena occur in the way that they understand things and their confidence in their own predictions. So with that, I'd like to thank you all very much for your attention. I appreciate it's a very broad-ranging subject space, so I hope you stay with it. And it looks like we've got plenty of time for questions. So thank you very much.
Thank you, Sam, for this very fascinating presentation. I mean, I have learned a lot, like getting a reminder about this slide scan and also all the recent development. Okay, guys, are there questions? I have actually a lot, but I don't want to spoil the chance to discuss with Sam.
Well, Hongbin, you're welcome to start.
Okay. Good. Okay. Let me maybe start. Okay, there's one question from Putra. So Putra, would you mind switch or unmute yourself and ask directly, or should I do this?
Yeah,
Oh.
okay. Uh, Thank you very much for your talk. It's very impressive. So I have one question. So what is actually the maximum resolution of the 3D microstructure that can be achieved with the methodology you develop? And the second one for your data set, what is the video or what's the image resolution as your input data set?
Well, if I understand your question correctly, from our side on the numeric side, it's the resolution is arbitrary. So we can see what the microscope can see. We can't go beyond what our highest resolution image is, and that's limited by the microscope. So that the techniques aren't they're not magic. So it's only reproducing the statistics as observed by the imaging data itself. So when you do super resolution of the or data fusion of the form that I've showed you, well, the resolution that's generated is the same as the resolution of the high resolution data set from the two data sets. So it's not going beyond the high resolution data set. Of course, there are some clever stuff that's been done historically about generating sub-pixel resolution from imaging, but that involves all kinds of interesting priors and ways of using the microscope. This is in a sense, a very brute forcey way of just applying the statistics from one place to another place. So yeah, I hope that answers your question.
Mhm. I mean, a continued question from my side would be, because on slide 31 also, you mentioned such kind of a local distinction when generating microstructure images. So then
Yeah.
the point would be how such local distinctions would influence the physical properties. Like, yeah.
Yeah, but it's a great question, and I think it depends on your application, right? There's not a,
Mhm.
there's not a universal answer,
Yeah.
and ultimately, um, y y with our generators, you can generate as much as you want, right?
Mhm.
I'm confident we can generate more than you can simulate,
Yes.
So it's not so much a question of the generator; it's more about the limitation of the simulation to ingest this stuff and simulate it.
Mhm.
And one approach that we've taken for one of our studies was, well, let's just generate 10
Mhm.
and simulate 10 and look at the statistics. And really, if you're simulating an appropriately sized volume, then the difference in performance is very minimal. But obviously, it's going to be super dependent on the materials and application that you're looking at. Some of them
Mhm.
might be very sensitive to this, in which
Mhm.
case, yeah, that raises all kinds of interesting questions.
Yeah. Okay. Sephora has a
Yeah,
question.
I should just mention that there is an academic partnership scheme. So Polaron, is out doing business with um, manufacturers around the world. That's very fun. But I'm really keen that we maintain our connection to sort of our academic roots. And so Polaron has an academic partnership schemes where we'll give institutions or give groups and institutions free access to the platform and some of our time to work with you to make sure you know how to use it so that you can apply our techniques, the segmentation, the 2D to 3D generation, the metric extraction, all that stuff. And we'll provide all the GPU compute, etc. What we want is for you to do good science and publish papers that say we did good science and we use Polaron to help us do it. That works for us, and hopefully that might be useful for some of you as well. So if you think that would be of interest, feel free to get in touch. And yeah, I'd love to hear from you.
Definitely. Okay. Sephora, can you please unmute yourself and answer the question?
Yeah.
Yeah.
Hi, first of all, thank you so much for your nice talk. And my is regarding the guns.
Uh-huh.
And what is the maximum size of 3D microstructure that can be generated using guns in terms of the number of pixels?
Oh, infinite, because it's trivial to make them identical on the edges.
Yeah.
Right.
Nice.
So I can the GAN takes a seed as its input, right? And the seed is spatialized, right? And so I can generate one, and then I can move the seed along and generate another one that perfectly stitches onto the previous one. So I can piecewise generate an arbitrarily large volume, and the pieces are just as big as your GPU RAM. and I can make them so I don't have to like fix the edges so they do stitch it. They just perfectly fit together with each other. So it's very satisfying. So we can make absolutely any size.
Mhm.
Okay, thank you.
Yeah, in this regard, so then when you see that for intersection in the middle, you can continue like both to the intersection, but then if you look at the three-dimensional features, so then would it also be continuous?
Yeah. It's absolutely perfect in 3D.
Okay, cool.
Yeah.
Good to know.
So
Yeah.
that was always a core part of you can see some results, some simulation results in the original Pause for Thought paper by Andrea Gaon Lombardo from 2001, where we show this like perfect continuity. And the other nice thing is for using the same mechanism, you can make it periodic if you want. So
Oh,
you can
yeah.
have the particles that disappear on the one side reappear on the other side, and that your physics-based simulations love periodic boundary conditions. Yeah, so there's a range of really cool things that we can do using these generative techniques.
Good to know. Okay, so Yan, so then would you mind unmute yourself and ask your questions?
Yes, hi. I'm currently on the way home, so I thought I was riding first because I was having problems with bad weather. But I can also ask it now.
Yeah, no worries.
Yes,
Go
you
ahead.
talked about LLMs and the regarding the Dunning-Kruger, for example.
Yeah.
But when I remember correctly, it's pretty difficult to tell how uncertain LLMs truly are. How was your approach there? I might have missed it during your talk as well, so
Oh, we're just
please bear
using
with me.
Negative log likelihood. So we just use the token level probabilities. There's like a broader research area around calibration where like how does
Yes.
self-reported confidence compare to its token level confidence? We're not getting into that. We're just using the token level confidence.
Okay.
Yeah, which
Okay.
like what does that exactly mean? And I think my answer is slightly glib, like, well, what do we mean when we say confidence? Like all of it's a bit slushy once we get to this level of
Yes.
abstraction. But I do think there are two clear ways to represent that. One way is token level confidence. Another way is a sort of Monte Carlo sampling of
Yeah.
predictions. And they tell not the same story, but they tell a very similar story. And you can say interesting things to it that affect the confidences more than the mean value, more than the expected value. So you can say to it like, hey, I've given you this limited data set. By the way, the function from which this data has been sampled is underdetermined by this data. And it gets less confident. So the model is able to respond both in functional form and in confidence to the things that you've said to it, which again, it's not surprising, but it's delightful. Like
Yes.
you're pleased to see the result. And an important thing that I should say is if I say to it something irrelevant, like here's some blah, 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 important stuff. By the way, the sky is blue and X equals Y and Y, blah, blah, blah. It doesn't change the predictions at all. So it also knows how to ignore irrelevant stuff, which again is very reassuring.
Okay. Okay. I have a second question, if you don't mind. That is a bit of a different topic.
Yeah.
You also talked about guns. How's your experience, or do you also have experience with denoising diffusion probabilistic guns?
Yeah.
And how is your experience when you compare both of them also in terms of small data learning? Because I have, for example, with my projects, the problem that I don't have a lot of real data. And so I was trying to figure out how to make the most out of it. Yes.
Right. Well, there's a few things to say. One of them is that, we started working on Polaron about 3 years ago. And obviously AI has moved on a lot since we published SliceScan in 2001. So the architecture underpinning Polaron is not necessarily what we were developing at Imperial, as you probably wouldn't be surprised to hear. However, even just at Imperial, we've been playing with diffusion and flow matching and these things. And they do have pros and cons. Like it's not a slam dunk once you're in this like interesting, like very low data regimes where there's a range of problems in this sort of segmented microstructure space that mean that it's not always obvious that diffusion is a better way to go. And I think, for the slice scan, for example, a single image, and of course, it's sort of slightly cheating when I say a single image, because under the assumptions of some degree of homogeneity, a single image is then cut into lots of little random patches. So a single image contains many images. It's, you couldn't train something on a single picture of a face because it contains one face, whereas a single picture of microstructure contains many local examples of microstructure. And we apply some data augmentations to these things, but I think, yes, SlideScan still works surprisingly well in these low data regimes. And if you can pass the test of a sort of image rep type analysis where you show that you're somewhat representative, then I generally find that the SlideScan works very well still. There's some other problems with diffusion, like you end up, like, it's very expensive. You're using
Right.
memory, and the way that you end up handling your data is very painful, and the 2D to 3D trick is also very painful.
Okay.
So I'm, even though it's kind of outdated technology, I'm still a big fan of the way the SliceCam worked.
Well, if you are specific, even diffusion models are already 10 years old.
Yes, yeah, exactly.
So the field is accelerating fast.
Yeah.
But okay, yeah, thank you very much for your answer.
Oh, my pleasure.
Yes. Okay. Any other question? If not, then let me ask the most urgent question from my side. So I like this inverse picture very much. This is also aligned with what we are doing in my group. So then you mentioned at the very beginning that you also want to cover or go back to the manufacturing step, right? So then this can be challenging because, like in order to get a particular microstructure designed, you need to really obey the thermodynamics. So then, like in order to design the former step or for the processing, do you have any clue how this can be done?
Yeah.
Yeah.
For us, this is not difficult because
Okay.
the conditions that we use, so we've got a generative model,
Mhm.
and then we have a conditionalized generative model.
Yeah.
Our conditions are not microstructure parameters. Our conditions are manufacturing parameters.
Okay.
Right. And so that it like steps around the problem. So we don't say, target 30% porosity. That's easy anyway.
Mhm.
We say target the mixing speed being 10,000 RPM, target the mass fraction of the components in the slurry being this, target this calendaring pressure, because we see the result of that. The training data is just microstructure that has gone through those manufacturing, the results from those manufacturing conditions. The relationship between them all and the resulting microstructure is very complex, and the physics to solve it is very hard. We sidestep all of that, and you just say, look, here's an image, and here's the parameters that caused that image to come about. Build that mapping, and that's what it does. So yeah, we know, well, we can say with a significant degree of confidence that our predictions are then manufacturable because they come out with the settings on the machines that you need to use to make them.
Okay, nice. This idea I haven't really thought about, to be honest. Good. We will try it out then. Yeah, because actually, yeah,
Try it out. I'll send you the link to the paper we published it. It's very satisfying to see that you don't need to do all this physics, right? The physics is, I think we are a long way away still from being able to solve the physics of mixing, coating, drying, and calendaring, right? In like a high resolution ray with particles that aren't spheres. And I mean, that's just so expensive and complicated. And I think the solution is to learn it from the data. And
For
so I
sure.
put that matter in the chat just now.
Yeah, got it. Yes, yeah, because the follow-up of Jan's question, in my group, we are trying to generate the 2D and 3D microstructures using the conditional control net. So then, like, then we could do this for 2D, and then we are now trying with the 3D, as you said, it is more challenging. And then, but on the other hand, the conditioning is a bit easier. But I haven't really thought about how to get the processing considered as a condition. But like the point you mentioned is definitely helpful. Cool.
Great,
Okay.
great. Oh, well, feel free to get in touch anytime.
Yo.
And then apart to everyone, people are always welcome to be in touch. I'm always happy to hear from people. So if you've got questions, please email me.
Yeah, definitely. Any other questions by any chance? Okay, good. If not, then Sam, thanks a lot. I have learned a lot really from the presentation, and then I'm looking forward to talk to you or meet you in some other occasions.
Great stuff. All right. Thanks, everyone.
Okay, so take care, guys. Bye-bye.
Bye-bye. Bye.